Hello everyone. Today is December 26 and it's time to open a new problem from LeetCode for our Coding Advent Calendar. Today's problem is a great example of how dynamic programming can improve our algorithm. Let's see the details. Here is a problem. Jump game. You're given an integer array nums. You're initially positioned at the array's first index, which means 0. And each element in the array represents your maximum jump length at that position. Return true if you can reach the last index, otherwise return false. And here is an example. 2, 3, 1, 1, 4, and we are here at position 0. We can jump 1 and appear here, but we also can jump 2 and be here, but from here we can do jump 1, 2, 3 and be in the end of our array. So we should return true. Here we are at position 3 and we can jump 3 and be here at 0, or jump 2, be here 1, and next jump will lead us to this 0. So, and the same for this. So we jump 1 and we have 2 here, which will lead us to position 0, and we will stay here forever because we cannot jump any further. That means we need to return false. How are we going to solve it? So this problem can be solved using recursion and dynamic programming. Let's do it without dynamic programming and later add it and see how this addition will influence on the time complexity and the speed of our algorithm. So let's define a helper function called canJump, but instead of accepting only initial array, it will also accept position at which we are currently stay. And all we do here, we will just return this helper function and pass nums there and position 0, our initial state. From here we need to check if I equal to the end of our array, right? We need to return true. Okay, if we jump too far, for example, and I is more than the last index, we need to return false. What next? Next we are going to try to jump, and depending on the value at current index position, we can jump into different number of steps. If the current index value is 1, we can jump only one variant, one step forward. If we have value 2, we can do 2 different jumps, 1 step forward and 2 steps forward. So let's do it like this. j equal to nums I, j should be more than 0, j minus minus. So we will iterate through different variants of jump. If can jump nums I plus j, return true. So if recursion gives us variant which returns true, that means we have a solution that helps us to reach the end of the algorithm, the end of the array. If not, okay, here we need to return false. Let's run it and try. Okay, it works, but this algorithm is not efficient at all, because the number of recursive calls will be huge and it will exponentially grow depending on how far we are in our recursion. So it is not very efficient. If we try to submit this value, this solution, we will get time limit exceeded, and if we have input like this, we are not able to solve it in reasonable amount of time. So we need to improve our algorithm somehow. And what we are going to do here is we will add dynamic programming part. We will add memorization. What we are going to memorize? We are going to memorize positions I which are checked already and they return false. And we will not try to repeat recursive calls from this position anywhere. So here, before we return false, we will mark this position as true, as visited. If we return true, then we don't need any values from this array and we will just return true. If we return false, we are going to memorize this index I. And what we need to do here, we need to check if dpi then return false. So we are not going to go into deeper recursive calls. And from here we need to create new Boolean array of this length. Let's try now. Okay, yes, of course we need to pass it. That's it. Problem solved. The time complexity of our first algorithm without dynamic programming is big O of 2 in the power of n. And after the improvement it is big O of n in the power of 2. A big difference. This problem can be actually solved in big O of n time and a constant space. Can you find this solution? Let me know in comments. See you tomorrow.